Okay, so in this section here, we're gonna start by going over, or I want to wrap this section by going over one last type of statement here. Now, in the previous video, we said that the contrapositive is always true, right? If the implication is true, right? So if this is a true statement, P implies Q, then not Q implies not P, always, right? That is always the case. Now, sometimes, but that's not to say, right? So let's take, for instance, the converse, right? So that's not to say that this is always going to be incorrect, right? In some cases, while not logically equivalent, both of these two statements might be true. Okay? So again, not logically equivalent, but the statements themselves could be true. Right? So if we are in this case where both of these are true, and again, not guaranteed to happen, but if we are, right, then this is what's called a biconditional. Right? So that means that if this is both true, then that we are in the biconditional situation, and that is P implies Q, and Q implies P. So P if and only if, right? So for example, think of the statement, a number is even if and only if its last digit is 0, 2, 4, 6, or 8. Okay. All right. And this works here, right? Let's say P, a number is even. Q, the last digit of a number. Is 0, 2, 4, 6, or 8. All right, and now think of the different if-then statements that you can make, right? So the first one is, if a number is even, then the last digit is 0, 2, 4, 6, or 8. True. All right, so we start with an even number. Think of all my evens, 2, 4, 6, 8, 10, 12, 14, 16, etc. Right, all of those end with one of those digits, so true. Right, and now we look at the other direction. If the last digit of a number is 0, 2, 4, 6, or 8, then it is even. Right? Also true. All right, so we have a proper biconditional statement. All right, now keep in mind this doesn't work just putting if and only if doesn't guarantee it to be true. So let's say an alternate statement here. A person is tall if and only if they play basketball. All right, where P being person is tall. And Q being person plays basketball. And we could see here, right? If a person is taller than they play basketball, well, that is not always the case, right? There are tall people that play other sports and not basketball, right? And even the people that do play basketball, right? If a person plays basketball, then they are tall. We know that is also not the case. There are a number of not tall basketball players, okay? So this is an example of something that, well, a false bicondition, okay? So just keep that in mind when the excuse me, when the converse is true from our implication, then we have a much stronger connection between P and Q, right? That connection is almost a definition, right? We can think of that if and only if as a stronger bond. And you can see from the way we symbolically represent, right? It's going in both directions, right? Where the implication just goes in one direction. Okay, so that brings us to the last kind of topic to wrap this up here, this idea about necessary versus sufficient. So it all starts with our implication. All right, if P implies Q, all right, so this is if P happens, then Q happens. All right. So doing P guarantees Q. All right. So P is enough. All right. So think of the statement, if you order dessert, then you pay extra. So we could say ordering dessert is sufficient for paying extra. All right, now necessary, this idea of necessary, we say Q is necessary for P. You cannot have P without also Q. Okay. So Q must be true whenever P is true. All right. So Q must be true whenever P is true. All right, so paying extra is necessary for ordering dessert. All right, so again, this idea that sufficient means enough, and necessary is required. Now, when this is for our implications, P implies Q. If we're dealing with a biconditional, if this is true, then P is necessary and sufficient for Q, and vice versa. Q is necessary and sufficient for P. Okay.